Salutation to our lecturer, Dr. Muhammad Azlan bin Ismail, as a lecturer for Mechanical Design 1. My name is Jesse Chung with matrix number BK191100142. The assignment asks for the material effect on the buckling load. The column has a square tubular cross-section with a wall thickness of 10 mm and a column length is 12 m. The column is axially loaded in compression and has pinned end. The mass of the column must not exceed 200 kg. Determine which metal in table 3.1 gives the highest buckling load. Also, calculate the critical load. From this understanding, we can find that the thickness of the tubular column is 10 mm. Hence, we can establish the effective length to be 12 meters since it is pinned ends. Noted that B is equal to the outer length, which is denoted by B, and H, the inner length, denoted as H, which is shown here. And B is established as H plus 0.02 since it adds both thickness on both sides as the total length. Also, we can determine the area of the cross-section by subtracting the outer length, the area of the outer length subtracted with the area of the inner length, which is added to the equation list on the top right corner. Next, we obtain the moment of inertia by using this equation as base times the cube height over 12. And since the size is equal, we can subtract the outer length minus the h to the power 4, and we simplify the equation as such. Next, it is known that the tubular column must not exceed 200 kg. From this understanding, we know that density plays a role in this equation. Hence, we know that mass is equal to density times volume, and also volume is equals to the area times the length of the tubular column. Hence, the equation will be as such. We then rearrange the equation so that we can substitute this density of equation into the moment of inertia, which is on the next slide. Substitute this equation with the equation on the top right as the density equation, which is rearranged, so it can be subbed into the moment of inertia. Next, we need to find the suitable metal, which is in table 3.1, based on the Euler equation, which is the critical load equals to the pi square times the modulus of elasticity times the moment of inertia over the effective length squared. By substituting the I from the equation 5, we can obtain the equation as such. Observing the equation, we can see that the modulus of elasticity and the density plays a role in affecting the critical load, as that when elastic modulus increase, the critical loading increase, while density decrease, the critical loading also increase. Hence, from the hypothesis, we can determine which metal we can pick to obtain the highest critical load, which is the nickel alloy has the highest elastic modulus of elasticity as 221 gigapascal, and the magnesium alloy, which has the lowest density with 1,770 kilogram per meter cube. With this property of metal, we can find the minimum length, the outer length, and the inner length for the nickel alloy, which is using equation number 4 as such. And we can obtain The inner length for the nickel alloy is 0.037 meter, while the outer length for the nickel alloy is 0.057 meter. Next, we obtain the magnesium length using the same equation. Can find it that the outer length of the equation is of the metal is 0.245 meter, and the inner length of the magnesium tubular column is 0.225 meter. As such, we can then obtain the critical load using the Euler equation by substituting the metal property obtained from the previous calculation into the equation. And we can find that the nickel has a critical load of 11 kilonewton, while for the magnesium alloy, we can find it to have a 244 kilonewton. Hence, magnesium alloy is used